Welcome back. In this video, I will talk about the measurement of surface tension using force methods, such as the detachment method or partial immersion method. Surface tension can be measured from force methods by doing force balances. For example, in the detachment method, we use the Noüy ring, where we measure the force that is required to pull the ring completely through a liquid interface. So we first submerge the ring into the liquid, then we slowly pull the ring out so that we can measure the force at the detachment. For partial immersion method, we use the Wilhelmy slide where we measure the force that is required to maintain the position of a solid which penetrates a liquid interface. So we have the slide that is within the water and we measure the force that is on the slide. To calculate the surface tension, we perform a force balance on the ring or the slide. The downward force is equal to the gravitational force or weight minus the buoyancy force that is upward plus the surface tension force that is at the interline of each surface that is holding the slide down. Mathematically, we have the force downwards is equal to gravitational force mg minus the buoyancy force, which is the density of the fluid, gravitational constant, times the displaced volume of the liquid, plus the surface tension force. If we assume that the surface tension sigma is uniform throughout the liquid, and the liquid fully wets out the solid, then the surface tension is equal to the perimeter multiplied by the surface tension. Let us first apply the force balance on the Noüy ring. The downward force is equal to the gravitational force that we can measure minus the buoyancy force. But because the liquid is at detachment, we can assume that the displaced volume of the liquid is approximately 0. So the buoyancy force is 0. For the surface tension force, the surface tension is an unknown, and we know the perimeter. The perimeter can be calculated by adding the inner perimeter, which is 2 pi times radius, which is big R minus R, and then plus the outer perimeter. The outer perimeter is 2 pi times big R plus small r, and we add them up. And then after simplification, we have the downward force is gravitational force plus 4 pi big R times the surface tension. From the force balance, we can calculate the surface tension before correction, which is the downward force minus the gravitational force divided by 4 pi, the radius. However, early investigators found out that the uncorrected surface tension is not exactly the true surface tension. So they added a correction factor to the surface tension term. The correction factor big F is dependent on the radius of the ring, as well as the density of the liquid and air, which is the two phases that we're interested in, and the uncorrected surface tension. The correction factor is also dependent on the ring's radius, small r. And after having this correction factor, the surface tension that is closer to the experimental prediction is equal to the downward force minus mg divided by 4 pi r, and then the correction factor multiplied. The equipment that we're using, the tensiometer, has this correction built in, so we don't have to calculate the correction factor again and again. We can also calculate the force balance for the Wilhelmy slide, where the downward force is equal to the gravitational force that we can calculate, minus the buoyancy force, which is the density of the liquid, which we know, the gravitational constant, which we know, and the displaced volume of the liquid. Displaced volume is equal to the volume of the slide that is submerged under the liquid, which is equal to the thickness times the width times the distance that is submerged under the liquid. Surface tension force, the wetted perimeter, is 2 times the width plus the thickness. And if we make simplification so that the thickness is way smaller than the width, then the thickness can essentially be And if we submerge the slide exactly when the distance that is submerged is equal to 0, the buoyancy term goes to 0. And the force balance gives us the gravitational force plus 2 times the width times surface tension is equal to the downward. Now in both force balances for the Noüy ring and Wilhelmy slide, we're able to measure everything except for the surface tension and the downward force. And to get the surface tension, we will need a method to measure the downward force. We can measure the downward force on the Noüy rings and Wilhelmy slides using tensiometer. Tensiometer is a device at which you can hang the Noüy ring or the Wilhelmy slide on a balance where it can measure force, the downward force or the upward force, which is essentially equal to each. And there's also a container for liquid, and you can move the liquid up and down so that you can detach the liquid from the ring or submerge the ring to the exact location where the submerged volume is equal to 0. From this device, we're able to get downward force, and therefore we can calculate the surface tension using tensiometer. In this lab, you will be using the Noüy ring and Wilhelmy slide to measure the surface tension of water, aqueous solution of sodium chloride, and aqueous solution of N-butanol. You will also measure the surface tension for aqueous solution of SDS and measure it as the function of its concentration. You can also use tensiometry to monitor the approach to adsorption equilibrium for dilute solution of the surfactant Titran X100. In this video, I went over the theory for force balance of the Noüy ring and Wilhelmy slide and how we can measure the downward force using tensiometers in order to calculate the surface tension of liquids.